My name's Nick Lariviere. I'm a kernel developer here at Wolfram Research. I work in the Mathematica Algorithms and R&D group. And today I'm going to be talking about dates and calendars. I'm going to try and give sort of a general overview, but then drill into a couple of individual points to try and hopefully give some interesting details to those of you who are familiar with the date framework, and also give enough of an overview for those of you who are still fairly new to the date and calendar systems we have right now. So I'm basically going to start with what comprises a general date and calendar framework to begin with. What are the components of time that we're interested in? And then I'm going to dive into the specifics of how we represent those in the Wolfram language, what the specific parameters we have are, and then drill into some of the sub-elements like date string elements, calendars, time zones, holiday calendars, et cetera. And then I also want to spend some time talking about some future areas of development that we're just starting to work on. So basically, one of the fundamental points of dates is that they represent a specific point in time. There are some caveats to basically everything I'm going to say here, because it turns out dates and calendars are kind of complicated, and we sometimes have to argue about whether general relativity or special relativity apply to specific applications. But in general, when we're talking about a date, it's a fixed moment in time. So today is a fixed date. The resolution that we care about may change, but there isn't ever going to be another one of today. And one of the things that can oftentimes be confusing is that there are two sets of time units that apply to dates. A general time unit is something that we consider a duration. So our units framework applies to this, where we have fixed relationships between units. In the unit framework, a month has a fixed value in terms of the number of seconds that comprise it. Whereas within calendar units, oftentimes these relationships are relative. The length of a month varies in different calendars. Another point I'd like to talk about is epochs and the year zero. Fundamentally, there isn't a universally agreed upon beginning of time. We can argue that the Big Bang is essentially the origin of time as we know it, but if our calendar years all start with 15 billion years ago, we're going to be working with really, really big numbers. So at a certain point, the way we choose to represent the start point of any time system is arbitrary, and we need to recognize that when we set up things in terms of calculations. Time zones are another important component of dates and calendars. They represent generally geographic regions where we have an agreed upon standard of what the current time is. Oftentimes these include daylight savings time, and generally they're regulated by local groups. It's not necessarily something that's universally agreed upon, which is why we don't have daylight savings time observed everywhere, and some countries don't conform to hour offsets from GMT. The last topic, which I'll talk about in more detail a little later on, is time systems, also known as time standards. This is where things like leap seconds come into play, and they deal with the way that we account for what the specific time is right now, and how we deal with things like variations in the Earth's rotation, because a day is not exactly 24 hours. There are variations, and certain events can alter that, and they change historically. Okay. So the 10-second overview of the Wolfram language is that we use a proleptic Gregorian calendar. Its epoch is at midnight, January 1st of the year 1 on the Gregorian calendar. We use a 24-hour leap second free clock, and we do not observe year 0. All of this is very consistent with the ISO 8601 standard for calendars, which I'll reference a few times. The main exception is that the ISO standard has a year 0. We generally don't observe that because historically we don't talk about a year 0 in the Western calendar. We go from 1 BC or 1 BCE to 1 AD or CE. The way that those standards are observed basically varies depending on country and particular implementation. We have a bunch of different ways we represent dates in the Wolfram system. The primary one, which hopefully you're all familiar with now, is date object. It's a wrapper that contains information that we haven't ever been able to store in dates before. It maintains information like time zone and calendar type, which we traditionally haven't been able to do anything other than infer. One of our classic representations is date lists, which are 6-element lists that show year, month, day, hour, minute, second. We have absolute times, which are a real value of a number of seconds since our epoch. Date strings, we have all kinds of different representations therein. More recently, we've added in Julian date, which is rather than a number of seconds since an epoch, it's a number of days since an epoch with generally a real value that includes the number of fractional days. And that's from a different origin point. Unix time is yet another purely numeric representation of time. It's based on the number of seconds that have happened since midnight, January 1st, 1970, Greenwich Mean Time. And then I've included sidereal time here, which is a slightly different representation. It relates to time in terms of your astrometric position or the relationship between the Earth's rotation and the sun. We also have some convenient constructors like now, yesterday, today, tomorrow that are quick references and ways to create date objects either to the specific moment or to a general day. We also have basic operations that you may do on dates. You can add calendar units to a date. You can compare the duration between two dates. You can generate a range. We also have date value, which lets you extract properties. We can do time zone conversion and calendar conversion. So now we're going to dive into hopefully something that's a little bit more interesting, and we'll get into some of the specifics. So date string has been around since the very early versions of Mathematica. In version 10.3 and 10.2, we've tried to add additional elements in, things like AD, BC, some of the ISO standards here that give us different representations of time. There's a whole bunch of elements, and included in being able to extract certain elements, we also have ways to format time differently. So the ISO standards provide guidelines because every different region tends to have different representations of how they show time. We have ambiguity of, whether of 10/10/15 is, or 10/5/15 is talking about May or October. And so the ISO standard basically says you always have a 4-digit year followed by a 2-digit month followed by a 2-digit day. And they also have standards that allow you to specify time as well. There are additional standards for specifying alternative representations. So instead of calendar, year, month, and day, you have year, week number within the year and day number within the week, or ordinal dates, which give just the year and the day of year. For date value, we can extract a lot of the same elements, but it gives us some benefit where we can specify different output types. So we can say, what hour is it right now? And it's actually returning an integer value for us by default. We can customize the different values that are returned. And it's oftentimes useful, so you can set up a quick utility function that takes a day or it takes a date as an input, and it can say, okay, I don't need to call to expression. I don't need to do anything fancy. I can just get the numeric value out and do a comparison. Date format is an option we have for date object, which allows you to specify the way in which the date is typeset. By default, we use our default value for date string format, which includes the short version of the date and time, and then we also add in the time zone explicitly, but you can specify a custom formatting, say you want to use ISO week dates. The fundamental date under the hood is the same, it's just the way in which we choose to present it is different. And that affects things like date strings, where you can say, I want when you format it explicitly, we'll inherit that formatting, but you can also override it very easily if you want it to be presented in a different form. Okay, now we're getting into interesting stuff. So time zones, if any of you are familiar with working with dates, generally time zones tend to be one of those things that people just want to tear their hair out with, because daylight savings time is something that's observed throughout much of the world, and it's something that just is insanely complicated for what it really needs to be. For most of Mathematica's history, we've had time zones represented as numeric offsets from GMT. And so, when you initialize your Wolfram kernel, it will look at your operating system or whatever system it's running on and figure out how far you are off from GMT. When you generate times, those will be returned based on that timestamp. And throughout the system, we have a time zone option that can be used to specify the output time. We don't have an option anywhere that says what the input time zone is, because most of the time, dates are done relative to your $ time zone. So if I type in a date list into a function, it's always assumed that it's in the time zone my system is in. And one of the big benefits of data objects is they're actually containers where we can say, no, this time is in GMT, and it can propagate throughout the system without me constantly having to modify what the assumed time zone is. Yeah, and so for example, we can, if we create a date that's assumed to be in our current time zone and we say we want the output time zone to be our time zone, it doesn't change. If we use block of our dollar time zone and we say our assumed time zone is something different, now when we turn it into time zone offset of -5, the relationship is now different because of our assumptions about what the input time zone are. Data object is slightly different in that the time zone option that goes into it is both considered an input and output time zone. If you type in a time zone, or if you type in a date and you give an explicit time zone, we assume both the input and the typesetting output you want for it are the same. You can always change it through functions like time zone convert. There are a couple of minor exceptions. Unix time and Julian date are both by definition in GMT, so they do not take a time zone option. You can't specify that I want this time to come out in Unix time in GMT -5 because by definition of the function, it's not something that follows the standards. Now at least for me, one of the most exciting things we've added in version 10.3 is support for non-integer or non-numeric time zones. That being, we can actually finally account for daylight savings time in the Wolfram language after 25 years. The way that we've done this is we've plugged into a large time zone database, and one of the complications with doing this historically is that the time at which time zones change is not necessarily constant. Legislation is changing the date on which daylight savings time starts or ends. Historically, they've also changed, so even though current local time here is offset from GMT by 6 hours or by 5 hours, historically we may have been offset by a different amount. And so there's a whole bunch of relational information we need to know about those time zones. We've extended this to include name time zones, so I can say, based on standard naming conventions, that I'm in time zone America/Chicago. As a convenience, we also have, if you start typing time zone, we'll have our autocomplete, which isn't running in this slideshow mode. We'll give you a list of auto-completed time zones so you don't have to remember them. We also have parsing for these, so I can ask Wolfram Alpha, I want mountain time, I don't know that it's America/Denver. We've also extended our entity framework to include time zone information, so I can give a location as the time zone. So when I say my time zone is in Bangkok, it will look up the time zone that is actually in Bangkok right now and assign that to the data object. And then we also have, they automatically adjust for daylight savings time, so the type setting here we have is in Central Time, or Central Standard Time prior to daylight saving time onset this year, and afterwards it's now indicating that it is in Central Daylight Time. We also, if you want to explicitly look up a time zone entity associated with a location, we have local time zone, so I can ask for the time zone in Tokyo. You can also, through the entity framework, get a complete list of all 463 time zones we keep information on. And we've also added a new system variable, which is your dollar time zone entity, which gives you the local entity associated with your computer's time zone offset. Next thing I want to talk about a little bit is holiday calendars, which in general are a slight extension of the idea that calendar time units are different than standard unit time units. So the idea of a holiday is a given day, but you can't convert a month into specific holidays. They're always relative. They're a type of day and they're a type of occurrence. And so what we've done is create a database of holidays for different countries and also for different exchanges, and we can do things like say, I want all of the holidays that occur during the week between two different periods. I can compare that to a different holiday calendar, such as the Chinese national calendar. I can compare that with a different exchange, like is on the New York Stock Exchange. One of the things that you can also do is specify a custom holiday calendar. So in this case, using a set of 3 different pure functions. I'm saying any day on which that we have May 9th is considered a holiday. So as long as the month parameter is 5 and the day parameter is 9, it's considered a holiday. So I can generate a holiday of different ranges across different years. Our recent updates to this have primarily been extending the data. So we've included additional information for different countries. We now have a much longer list of available holiday calendars. We've also added additional exchanges, such as the Tokyo Stock Exchange, for some of our financial computations. Additionally, we extended the day framework, which is related to the date framework, into some of our more general functions. Previously, if you wanted to compute holidays, you could only do them on days without a time component, and we've basically generalized that so we can extend things more easily. So I can say to add 250 business days to today on different calendars, and we can see that there's a difference in the number of holidays that happen between the Chinese national calendar and the United States calendar. Right. Another aspect of dates that can be a little bit complicated is calendars. I said earlier that we use a proleptic Gregorian calendar. That means we extend the Gregorian calendar back prior to its official adoption in the 1500s. Oftentimes, there can be confusion about this because the way in which the Gregorian calendar was adopted, there were basically different time periods where we switched from Julian to Gregorian. It caused a whole bunch of havoc in Great Britain in the 1700s, and people rioted in the streets because we basically lost 2 weeks of time. The only real difference between the 2 calendars is the way they account for leap years. The Gregorian calendar is more accurate to the Earth's rotation, but in addition to those calendars, we've also taken 2 of the more widely used calendars throughout the world, which are the Jewish and Islamic calendars. And so I can generate date objects on those calendars for today that include typesetting for the month and day names. And also you can do conversion from a given date object in this form. So I can say I want to take today and convert it to the Jewish calendar directly within a date object. And I get a date list form, but because it's wrapped in data object, we can track the fact that this isn't a Gregorian calendar. We're not talking about some day really far in the future. It's the same day as today. It's just represented differently in the language. A couple of notes. Oftentimes with calendars, we get into fuzzy areas where, for example, the Islamic calendar, there are at least 4 major different variants of it that all have to do with the way in which we observe lunar cycles. The way we represent it in the Wolfram language is the most widely adopted internationally. It's the lunar Hijri calendar, and basically it's one of the tabular calendars are more recent adaptations. They fall more in line with standard computational systems. We don't have someone going outside and determining when the new lunar cycle started, which is the case with some of these older calendars or some of the calendars that are used in different places, which make them really hard to use computationally. And so hopefully in the future, some of the tabular calendars will be more standard, but for the time being, we try and have the language be as accessible to as many people as possible, so we've generalized it based on that information. For calendar operations, the main operation we end up doing is doing calendar conversions. So I can take a given date and convert it to different calendars. We also support it as an option in different functions. If you're not using a date object, for example, and you just want to have a date range using date lists, you can specify a calendar type. And if we compared this to the same calendar being generated on a Gregorian list, we'd get different dates because of the ways that the weeks operate within the months. The length of an Islamic calendar year is not the same length as a Gregorian calendar year. Okay, so I want to get into an application of taking some of this information and actually trying to apply it. So I'm going to glaze over some of the history here, but traditionally there's the Mayan calendar as we know it is generally broken up into 3 different parts. Generally, when someone talks about the Mayan calendar, they're talking about the Mayan long count calendar. It's the only calendar we can really relate to in terms of Western calendars because it's the only one that has a finite cycle. Both the Hab and the Tzolk'in calendars are cyclical, but they basically don't keep track of where they are within time. Once it finishes a cycle, it just starts over, so we don't know how many cycles have elapsed. There's still some dispute about exactly when the Mayan calendar started, but in this example, I'm going to be using the most widely recognized epoch date, which is set by a Goodman-Martinez-Thompson correlation. Basically, one of the things that makes the Mayan calendar interesting compared to Western calendars is instead of year, month, day, we actually have 5 different parameters. We have kin, which is analogous to a day, unal, which is 20 days, a tun, which is 18 unal, a katun, which is 20 tun, and a baktun, which is 20 katun, which basically ends up being a 144,000 day cycle. And basically when we talk about the Mayan in 2012, when everyone was talking about the Mayan calendar events, that was basically the Mayan long count calendar cycling through a new period when the Mayans believed that every time the cycle finished, that basically the world was destroyed and created again. So there are a bunch of different ways we can represent the epoch. What I've chosen is to use a modified Julian date, basically to simplify the example a little bit. But basically we want a fixed point in time where we know the relationship between the Mayan calendar and another calendar system. So we're going to use the Julian date because it already increments once for every day. So I'll choose this specific date, which is generally considered the most widely accepted by scholars, which is basically the year 3144 BC on the Gregorian accounting for calendars. And the way that we do conversion, because these cycles are fixed, we don't have to worry about leap months or anything like that, is we basically just add our epoch to the number of each of the different parameters multiplied by their scalar factors. And so for a basic example date here, we can say that it's the 7th baktun within the cycle, 17, 18, 19, 2, and we get a fixed number. This is the number of days relative to our epoch. What we can do then to convert to convert them to a Gregorian date is basically use the features we've already built into from Julian date, where if we give it a Julian date, it will convert it to a calendar date for us. So I can look at that example input and figure out when that would be on the calendar year or on the Gregorian calendar. So it'd be April 30th of the year 1. And I've specified a time zone here just because by default from Julian date will give me a date back in my current time zone, and I'm at this moment not really concerned about accounting for daylight savings or anything else relative to these conversions. Okay, so basically all we need to do is I've set up this utility function here where we basically are just multiplying by the calendar units. I can add an extra layer in here and say that I want to take from Julian date of the input here, and then I'm using the date value function with a date object specification to say I don't actually care about what time of day it is. We're basically just looking for calendar to calendar conversions here. So I can put in a arbitrary Mayan long count calendar day and I get back a Gregorian calendar date. Yay. Now, most of us don't have a lot of reference point for Mayan long count calendar days to try throwing in here to actually check it, so we want to go in the reverse direction. The basic operation is the same, again, because this calendar is cyclical. We don't have to worry about leap years or anything like that. We basically take that Julian date and then we just subtract the epoch, so we have a fixed number we know relative to those cycles, and then we're just taking the quotient and remainder by each of the unit factors here. So we're figuring out how many baktun there are, katun, tun, uinal, and kin, and then we can just return a date list here. I've done a floor operation at the end, basically, again, to chop off anything related to the time within the day, just to simplify the example. But I can look at my epoch day and make sure, indeed, if I take that Julian date and I feed it in, I get back the epoch date within this calendar system, so 00 all the way down. I can also take a given date here, so I can say I want to look at April 1st and turn that into a Julian date. I can feed that Julian date in, and then I get the appropriate Mayan long count calendar. If I want to convert from any given date format, and I don't want to necessarily have to feed it into Julian date, I can basically make an extra wrapper function here, which says it's accounting for time zone offsets, and basically just calls Julian date, or a modified Julian date, and then calls my utility function, so I can type in a date string, and it will turn it into the long count calendar date. I could give it an absolute time. I can check today and I get the same result. So because of the way that we uniformly handle dates, if I can feed it into one of these utility functions like Julian date, it basically just handles everything from there for me. And then I can do a sanity check just to make sure I actually am round-tripping dates. If I turn a Gregorian calendar date into long count and then convert it back, I'm getting back the same date that I put in. Okay, so that's basically an overview of what we already have in the system. I'm running a little low on time, so I'll give basically an overview of the 3 things I think we still need in the Wolfram language. One I alluded to earlier is handling of time systems. One of the complaints we occasionally hear is that the Wolfram language doesn't have a good way for handling leap seconds. Right now, that's done intentionally because there are a bunch of different leap second standards. There's UTC-0, which is generally not widely used anymore. UT1, or Universal Time Standard 1, is generally the best standard, but it isn't current. Most people use UTC, which is an estimate of UT0. There's TIA, TDT. There's a whole bunch of different things going on. And we want to make sure we can address the system as widely as possible, because it does matter for things like astronomical calculations, the way in which you account for, relativity when it comes to averaging the different atomic clocks as they're spaced around the globe. There are things like, earthquakes can change the rotation of the globe. There's a bunch of different things going on there, but it's an active area that we're looking at trying to develop. Another thing we'd like to add right now that I alluded to a little earlier is generic or recurring dates. We don't have a native language representation to say February 1st of any given year. We can say it for a specific year, but we can't say all February 1st. So that's something we're interested in pursuing, and we've got some ideas, but it's something that we definitely appreciate feedback if it's an application area that people are interested in. And then the last example is also time spans. So being able to, we can explicitly generate a list of dates, but we don't have a great uniform way to represent this event started on this date and ended on this date and happened all throughout. There's also ambiguity of it happened sometime between this point and this point, so there's a through versus during ambiguity. And we're trying to take all of those into account so we can have a good system that works for all application areas. I'm unfortunately pretty low on time here, but I wanted to pitch Gosha's giving a talk right next door on time series processing in a couple of seconds here. But that's definitely an application area I'd suggest, and later on today, Min is also giving a talk. I've included some links to some of the things I discussed, like the ISO standard, also a link to the IANA time zone database if you're interested in finding out more about time zones. I've linked Nachum Dershowitz's book here as well, which is great if you want to get into calendars. And I've also included my email address if you have any questions or if there's anything you feel like we're not addressing in the time system yet, definitely feel free to drop me a line. So thanks, everyone.